All right, so then let's start on chapter 6. So what chapter 6 is talking about now is sampling distributions. So let's first try to understand what a sampling distribution is, how that's different from the distributions that we've been talking about before, and then that will also help us introduce why some of these formulas are different. All right, so let's go back to that example where I said, I'm going to hand out pieces of paper, and on these pieces of paper, you're going to write down the average number of times that you call your mother in a month, right? So if you guys remember back to that discussion, we first started using that for our discussion about what a distribution is, and that's when I first started introducing the idea of like Connect 4. And what we said was that you can call your mother somewhere between 0 times in a month and 30 times in a month. And then I would simply just, collect these pieces of paper again, go through these pieces of paper, and suppose that the first person told me that they called their mother 5 times in a month, I'll make a dot above 5. If the next person said they called their mother 15 times in a month, I'll make a dot above 15. Maybe the next person was 28 times a month. And then if I came across another person that said that they called their mother 15 times in a month, I would simply just make a second dot above 15, right? So again, kind of like the whole Connect 4 issue. If I went through the entire class and did this, I have no idea, again, what that distribution would look like, but we can just, suppose that it looks something like this. And then this is when we said, all right, well, here, if we simply just recorded these numbers, like here, this is the number 1, this is the number 2, and then 3 to measure the heights of these different things. This wasn't technically our probability distribution. Instead, if we called this, this was more of a frequency distribution. If we wanted to make it into a relative frequency distribution, what we could do is we could just simply figure out how many dots that we have here. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So here this would be like 1 out of 17, 2 out of 17, 3 out of 17. And then this was going to be our probability distribution, right? Or what we're since have just been referring to as a distribution for short. All right. This is kind of where we left off, especially for discrete random variables. For continuous random variables, we simply just said that you can imagine like the tops of these dots being connected by some kind of smooth curve, and then that would just be a basic representation of a continuous random variable, where you didn't necessarily have to fall into these individual buckets. You could also fall in between these numbers somewhere, and even in between these numbers somewhere, that graph would still be defined. All right. That's a quick high-level overview of the types of stuff that we've talked about so far. Now what we're going to see is, how is this graph different, right? How is this distribution different if we're not looking at what we have been looking, but instead we start looking at a sampling distribution? And if we start looking at a sampling distribution, this is how this thing is going to start getting different. Suppose that I didn't give a piece of paper to every single one of you. Let's say that I first started putting you in groups, and maybe I'll group you guys in groups of 4, right? So I'll put you 4 together, and then I'll put the next 4 together, and then the next 4, and then the next 4, right? And I say, hey, instead of recording every single person's number on this piece of paper, what I want you to record on there is the average of your group, right? So then you all told each other your numbers, you figured out what the average was, you wrote down that average on that piece of paper, and then I collected those pieces of papers, right? 1 piece of paper per group. And then what I did was I started recording a dot on here. But now what this dot does not represent is it does not represent just one person. It represents a group of people, right? More specifically, it represents the average of that group of people. Right? Is everybody good with that? So if I wanted to do this, I could say, hey, maybe I'm going to call this the average of group number 1, right? And what I did right here is, first off, what's the symbol called again? X bar. And what does X bar represent? The sample mean, right? The sample mean, the sample average. So let's say that here I say that this is the average of the first sample, or the average of the first group. Maybe this dot over here is like the average of the second group. Maybe this dot over here is like the average of the third group. And I don't know, maybe this dot over here is like the average of the fourth group. And so on and so forth for however many averages that we have, right? Clearly, if we're plotting the averages of these groups, we're not going to have a single dot up here for every single person. So if we're consolidating people, we might not have quite as many dots up here. However, what we're not going to have is, we're also not just going to have 4 dots up here, right? Why aren't we just going to have 4 dots up here? Let's also talk about a slightly different concept, and that is this. What we want to make sure that we're doing is we're not just taking the 4 groups of people that I could make in this class, but what I want to do is I want to create all possible groups of size 4, right? So what I just did then was I made one group of size 4, a second group of size 4, a third group, and a fourth group of size 4. But that's not all possible groups that I could make. What I could do is I could say, hey, I'm going to leave you off, and because I'm leaving you off, I have to include another person. And then I'm going to go through, I'm going to create groups of 4, and you're just going to be in with that group that's all the way in the back. Those are different groups of 4. Then we go through the same process again, and I say, hey, record the average of your group now that you guys are in slightly different groups, and then I can go on and I can plot those numbers, right? But then I wouldn't be different, right? Because so far I've just let Josh off, right? Now I can let Cherise off too, and I can make it the next group of 4. And then go on through, and then you two would just be in the back group, right? You would eventually end up with being in a group with everybody in this class at least once. Right? Does that make sense? Because I could just keep on going through and keep on making groups of 4. Is everybody good with that concept? So I would still have a whole bunch of dots up here, right? But now each one of those dots would be a distinct group of 4 people. Does that make sense? All right. So I'm just giving the example for a group of size 4, right, where our sample size is size 4. What I could also do then is just go through that whole exercise again and just make everybody in groups of 3 and in groups of 2 or in groups of 5, or whatever size that we wanted to, right? The important aspect about this graph then is that I plot all possible samples of a given sample size. That I'm only going to plot the dots up here if there's 4 people in the group. If I change up the group size to a group of 3 people in a group, I can no longer use this graph. I have to make a whole new graph for itself, right? That are just going to have sample sizes of size 3. Right? Everybody get the gist of what we're doing differently up here for sampling distributions versus those distributions that we've been working with in the past? All right. So then, if we're working with sampling distributions, there's a couple of other things that we obviously need to talk about then. Here it just says that a sampling distribution is a probability distribution of some statistic. What does it mean to be a statistic again? What does it mean to be a statistic? Where do we get statistics from? What is it? Okay. Where do we get statistics from? Nope, you're close. The other one. Sample, right? We get statistics from samples. Anything that we're calculating out from a sample is called a statistic. And what do we call stuff that we calculate out from a population? Parameters. Awesome. So we get statistics from samples, and we get parameters from populations. Here, what we're doing is we're creating groups of people within the class, right? So these are individual samples. The example that we went through was that you guys tell me your average of your group, but I could ask you to record any other statistic that I wanted to, right? I could say, hey, instead of writing the average on this piece of paper, write the mean or the median on this paper, right? Then you would just say, hey, let's figure out who's the middle person or the average of the 2 middle people, and then then we would record that number instead. I could also ask you to tell me what the largest value is, right? I could pick any statistic that I wanted to. We would then plot those statistics on this graph, and then that would simply just be a sampling distribution. All right. Then, obviously, if we have some distribution of numbers, we can also calculate out the mean of this distribution, and we can calculate out the standard deviation of this distribution. All right, this is a little bit more difficult, right? Let's think about this here for a second. I think everybody's on the same page that each one of these numbers represents the average of a group of 4 people. But in the end, these are just going to be numbers as well, right? Like if I took a group of 4 people and said, tell me the average time in a month you call your mother, you might say it's 7. Well, group number 1 might have a number of 7, group number 2 might have a number of 10, group number 3 might have a number of 13. What I can also do then, right, like let's say this is the number 5, let's say this is the number 7, this is the number 18, and this is the number, 20, right? I could take the average of these averages, right? The average of the averages. So then I could take x bar 1 plus x bar 2 plus x bar 3 plus x bar 4. And I could divide that by 4. And now I'm taking the average of each group's average. Everybody good with that? All right. The average of each group's average has a very special symbol, and that is this. It's the average of each group's average. So we're going to call that as mu sub x bar. It's the average of all the sample averages. Everybody good with this concept? The average of the sample averages? Well, if you take the average of all of the sample averages, then here we have a very, very, very important statistical concept. And that is, if you take the average of all of the sample averages, it's going to be equal to the population average. Is everybody good with what that means? Because that's an extremely, extremely important statistical concept. Let's go through that exercise, right? We're definitely going to get to that one too. But if you guys understand this one, then understanding this one's going to be really, really easy, right? So let's go through it and make a picture of what exactly I mean, right? So here in this class, we currently have, 14 people here today. Let's just suppose that there's 16 people here today, right? And then these 16 people, what I'm going to do is I'm going to split them up into 4 groups. So we have samples of size 4, right? So then you can imagine here being one person in here. Here's a second. I'm going to go through this here real quick, and I'm going to make this into an elaborate picture. So I'm going to draw all these people out. I know I'm spending a lot of time on this, but this is actually a really important concept, and one that a lot of people struggle to grasp. All right, so this is our class. Hey, class. And then for some reason, maybe I'm in one of these groups. Hey, maybe I'm making the 16th person, right? There's technically 15 people enrolled in this class. But anyways, so here we are. We're broken up into groups. And now what I can do is I can give each one of us a little piece of paper, and I can say, hey, write your number of how many times in a month you call your mother on this paper. And let's say that this person writes the number 17, this person 18, this person 5, and this person 6, and so on and so forth. Right? Everybody get that? So here, might as well just do it. Here, this person calls her mother 30 times, like that. That person's like, awesome. 2, 1. All right, I'm having too much fun with this picture. All right, Everybody get the gist, all right? You're writing your number on a piece of paper of how many times on average in a month you call your mother. All right. Now what we can do is, we can do two things, right? Let's start off and say, hey, maybe I want to calculate out the class's average. Well, if I want to calculate out the class average, I would take each one of these individual numbers, and I would add them together and divide by 16 because there's 16 people in this classroom, right? So I would take like the number 17. I'm not going to write all these out, obviously. Plus 5, plus 6, and then I would go over to the next group, plus 10, and so on and so forth. And I would divide this by 16 because there's 16 people here. And that would be the class average. All right, now I'm going to set this number aside, whatever number we get right here. Since this is an entire population, though, I'm going to call this number mu. Right? It's the population average. Now what we can also do is we can take each group, and each group can tell us what their average is. So I'm going to call this group number 1, this group number 2, this group number 3, and this group number 4. And each group can now tell us their average. So I'm not going to do this for all of them, obviously, but if we take 17 plus 18 plus 5 and plus 6, and we divide that by 4, that's going to give us our group average, right? So each group's average, I'm going to call these numbers right here. Well, now if we want to figure out the average of our sample averages, just like I had on the previous page, we would have this right here. We're going to take all of the group averages and we're going to divide it by the number 4, right? Now, the important mathematical concept that we're calling this is that we're saying, hey, first the symbol for this is the average of all of these sample averages, all of the group averages. And what we're saying is that mathematically, if we go through this exercise, the number that we calculate out here has to be equal to the number that we have up there. Right? It just so happens to work out that way so that mu is equal to mu sub x bar. All right. Is everybody good with that concept behind this equation? That's super, super, super important. It allows us to do all sorts of things. Now, what this is saying is this. If we calculate out the standard deviation of all of those groups, and then we take the if we calculate out the average of all of those groups, and then we calculate out their standard deviation, so here, instead of calculating out their average, instead we're going to calculate out the standard deviation of those numbers. And you guys know how to calculate out standard deviation of 4 numbers. Now, if we calculate this out, that's not going to be equal to the population standard deviation, so the standard deviation of these 16 numbers. Instead, we're going to get this right here. That the standard deviation of the sample means is equal to the population standard deviation divided by the square root of n. All right, so that's the theoretical background information for, or at least describing that in terms of pictures for these two things. Why exactly this works out is actually very, very theoretical. We're definitely not going to get to that in this class. But one of the things that you absolutely have to do, your success on Chapter 6 completely depends on, or almost completely depends on, whether or not you remember these two formulas. Right? These two formulas are on your formula sheet. So you have to at least remember like when you apply these formulas. Right? All right. You had a question?
Yeah. So, like on the first exam, you had the keywords to use the same formula, like get in that or whatever. Do you think with these components, those would also work?
Yep, there sure is, and we're going to get to that. I'm going to make sure that I highlight those buzzwords to you guys as well. All right, so let's go through some examples of when we use these two formulas. All right, examples of calculating the mean and standard deviation of a sampling distribution of means, right? So our sampling distribution is comprised of our sample means, and we're trying to figure out the mean and the standard deviation of those things. The average sale price of a single-family house in the United States is $240,000 with a standard deviation of $42,000. A random sample of 36 single family houses is selected, let X bar represent the mean sales price of this sample. All right. So here's a very, very, very good indicator for when you have to apply these two formulas, right? Mu is equal to mu sub X bar, and sigma sub X bar is equal to sigma divided by the square root of n. Something that's definitely going to help you guys determine when you have to apply this is the fact that you have some random sample with a sample size. It's, especially for this class, the way that the past common finals have always been worded is if you see some kind of random sample number in here, then your chances are you're going to be dealing with a sampling distribution. But let's give a little bit more better way of identifying how we approach these problems. Let's think about this. If we look at this, we have some mean and we have some standard deviation. And we're looking to try to find that, what are we trying to find? The average sales price of single family home. Oh, okay. So here we have a mean and we have a standard deviation. And we're trying to find the mean and the standard deviation of our X bar, right? So here it straight up tells us that we're trying to find the mean of X bar and the standard deviation of X bar. Or another way of saying that is mu sub X bar and sigma sub X bar. So this problem right here is telling us to find mu sub X bar and sigma sub X bar. The one where the road I was starting to go down was what we're going to do in part B. But in part A, it literally just tells us to find these two things. So we're trying to find mu sub X bar. From our formula, we know that that's equal to mu. So then what number are we going to try to identify in this problem? The average, and what's the average? 240,000. So for this one, we're literally just copying down a number. It's just the average. For sigma sub X bar, according to our formula, we know that it's sigma divided by the square root of n. What's sigma in this problem? $42,000. What's little n equal to? 36, because little n represents our sample size. So for this one, we're simply just doing the simple arithmetic. Take the square root of 36, you end up with 6. 42,000 then divided by 6 is $7,000. And there we have our two answers. So, the reason why I tend to go through chapter 6 rather quickly, especially this beginning part of it, I tend to spend a little bit of time on the theoretical stuff. But once we start going through these examples, the reason why I go through these rather quickly is, for this one right here, we're literally just copying down a number. Right? For mu sub X bar, we're literally just copying down a number. For sigma sub X bar, we're simply just doing the simple fraction. That's it. That's all we're going to do, and that's what we're going to do a couple times for part A of these problems. All right, is everybody good with part A? All right. Now, part B, that's the one that, like I said, I started to go down this road, but I realized that this wasn't it. But now we are going to do this. Here we're saying, what is the probability that the sample mean sales price X bar is between 235,000 and 252,600? Let's first try to take this statement B from an English sentence and try to put it into math symbols. How would we put this thing into math symbols? P in parentheses, because we're saying, hey, probability that. So we're going to have P in parentheses. And what are we going to have in parentheses? So I heard X bar and I heard 235, right? What's with 235? 800? Right, we want to have our X bar in between these two numbers. Good. So here we're going to have 235,000. And then here we're going to have 252,600. Then, 235,800. Thank you. So now we're going to have our X bar in between these two numbers, right? Does that make sense? Does it matter if it's less than or equal to? No. Right? Everybody's good that we just put this into math symbols then? Now this should start looking extremely familiar to you guys. What's the only difference between this and what we just got done doing? It's an X bar, right? So the process, once we get to this point, is the same process that we did before. What was our first step in the process that we did before?
Even out the formula.
Say again?
You even out the formula.
You even out the formula.
Like, you do on one side, you do the other.
Good. You do. So what's your objective between doing stuff on either side of this?
Find z-score.
Good. Changing it into a z-score, right? Which is what some of you said. So here, we're going to try to change this into a z-score. So our first step always was, is this a z? No, it's not a z. All right, then let's change it to a z. So if we want to change something to a z, what we've always been using so far is our z formula for x minus mu over sigma. However, we don't have x. We have x bar. So, therefore, here, what we're going to do is we're going to change this to an x bar. However, now that we're with an x bar, we're no longer just in a distribution, we're in a sampling distribution. Right? Does that make sense?
Is that allowed just to put an X bar in instead of z?
Yes, because we're not quite done doing this, manipulating this formula yet, right? Because now we're not dealing with a distribution, we're dealing with a sampling distribution. So for the sampling distribution, we also then have mu sub x bar, and we also have sigma sub x bar. Right? We're no longer dealing with just mu and no longer dealing with just sigma. Now that we're in a sampling distribution from the previous page, we know that our formulas need to be mu sub x bar and sigma sub x bar. Everybody good with this? So now what we have is your book kind of presents us as, here's a brand new formula. You need to know this formula. But it's not, right? All it is that we have the same old formula that we had before. We're just changing the symbols around a little bit, right? Giving them like a new name. And it's basically the same thing that we're doing before. Here's the one big catch. And this is where people tend to get these problems wrong in this chapter. If you do this right here, remember that sigma sub x bar is equal to what? Sigma divided by the square root of n. And we also know that mu then is equal to mu. So therefore, we could just have mu right here, because those two things are the same. Therefore, the one big catch that people always have is this. They forget to divide by the square root of n. The most commonly made mistake in Chapter 6 is that whenever people convert stuff to z values, they forget to divide by the square root of n when we're dealing with a sampling distribution. So here, make like stars or exclamation marks, or I don't know, write yourself a note that careful, like this is the most commonly made mistake. So now, Albert, going back to your question before about the previous chapters having buzzwords and stuff, if we go back to what the buzzword is for this chapter, and this is why I keep saying I started to go down this road, is whenever you see something that says that we have a sample size, especially if we're dealing with a random sample of stuff, well here, we've seen stuff like this before. The only difference now between questions like this and what we did in Chapter 5 is that these questions start to have a sample size in them. Whenever you're dealing with a sample of stuff, especially if it's a random sample of stuff, we're going to be dealing with our sampling distributions. So here, this right here, it's like your buzzword, so to speak, of saying, hey, I need to start using X bars.
Okay.
Now, what we're going to start doing here is going to be really, really similar to it. The only difference, really, for like 90% of stuff that we're going to do in Chapter 6 is that if we have a sample size up here, now we have to divide this by the square root. Cool? All right. Other than that, this is exactly the same stuff that we were doing in the previous chapter. What we're going to do is we're going to convert this x bar to a z by subtracting the mean and dividing by the standard deviation. But now we have the sub x bar subscripts. Whatever we do to one side of the equation, we have to do to all sides of the equation. So then we're going to have 252,600 minus mu sub x bar divided by sigma sub x bar. Now what we've just done is we've just converted this middle term right here into a z value. I can plug in these values right here. For the mean in this problem, we already said was 240,000. And we already said that sigma sub x bar was equal to 7,000. Right, I know I'm going through this now a little bit more quickly, but I think now it's just really just arithmetic, because we should be able to calculate out the numbers on the left-hand side and on the right-hand side. And if you do this, we should be getting the numbers negative 0.6 and 1.8. And if we do this arithmetic, we should end up with 0.689. So I know I went through that last little bit a little bit quickly, but the only difference that we have is literally this step right here, and that is for sigma sub x bar, we need to substitute in 7,000 and not 42,000. How do you guys feel about this so far? You guys see the similarities between this and Chapter 5?
I just think the X bar uses a little more extra.
The X bar, yeah, you just have to do one extra step, right? Divided by a square root of it. All right. Then take a minute or so for yourself, or maybe 2 minutes or so for yourself, and see if you can do number 2 by yourself. Does anybody need a little extra time? Alright, then let's do this together. So the cholesterol in the blood of women aged 20 to 55 in a particular country is normally distributed with a mean of 212 milligrams per deciliter and a standard deviation of 45.2. What is the probability that the mean cholesterol level in a random sample of 20 such women is between 200 and 240? Alright, so we know that we have a normal distribution, and what we're trying to figure out is what is the probability that a random sample of 20 of these women is between 200 and 240. So between 200 and 240, trying to figure out that the mean cholesterol level, so X bar, is between these two cutoffs. All right, is everybody good with that? If I take that English sentence and write it like this? All right, well then if we have this then, we're going to go through the same process that we've always been doing. We're going to see whether or not this right here is a Z. It's not a Z. So the way that we're going to convert it is we're going to try to use our formula Z is equal to X minus mu over sigma. But now we recognize that we're talking about the mean of some sample. So therefore we're going to change this to an X bar. We're going to change this to a mu sub X bar and this to a sigma sub X bar. But again, the most important thing right here, the one that a lot of people usually forget, is that the sigma sub X bar is equal to sigma divided by the square root of n. So I'm going to write that out explicitly in this problem now, because now what we're going to have is we're going to have X bar minus mu sub X bar over sigma divided by the square root of n. But whatever we do to one side of the equation, we have to do to all sides of the equation. So we have 200 minus mu sub X bar over sigma divided by the square root of n. All right, is everybody good with this so far? So now we can start plugging in numbers, because what we have done now is we've successfully converted this middle term to a Z value. We're going to have 240. What's mu sub X bar? 212, right? Because mu sub X bar is the same thing as mu, the population average. So therefore we can just substitute in 212 for this. What is sigma equal to? 45.2. Is this good like this? Now is everybody good with this? Alright, so then what I'm going to end up with is, did I do this one? Sure did. I got negative 1.19 and 2.77. And then if you look those two numbers up and subtract the smaller from the larger, I got 0.8802. Everybody good with how to get 0.8802? Because literally, once we substitute in this divided by the square root of n right here, it's just back to a chapter 5 type problem. Alright, any questions about number 2? You guys getting the gist of these problems? Alright, then let's go on and do another one. Take maybe 2 or 3 minutes for yourself and see if you can do both part A and part B on question number 3. Okay, does anybody need a little extra time? All right, let's do this one. The weights in pounds of paper discarded each week by households in Tucson, Arizona are normally distributed with a mean of 9.43 pounds and a standard deviation of 4.17 pounds. What is the mean and standard deviation of the sampling distribution of the mean of a random sample of 12 households? So we're asked to find the mean and the standard deviation of the sampling distribution of the means. So we have the mean of the means and the standard deviation of the means. If we're looking for the mean of the sampling distribution of the means, what number are we going to record?
9.42.
And if we're looking to find the standard deviation of the sampling distribution of the means, what are we going to do? Everybody good with this? And then this comes out to 1.2. Everybody good with this? Generally speaking, whenever you're going to see a question on a test, it's always going to say something like, use this information for the following two questions. And the first question that immediately proceeds after that is going to be one like A. Right? So those should be the give me questions on the exam. Right? Because one, you're just recording a number, and the other one, you're just doing some kind of simple fraction. Then the second problem of that kind of setup would be something like we see in B. And here, what we see in B is we're asked to find the probability of something. So we're going to find the probability of something. And that is that the mean is between, so here we have the mean between 10.1 and 12.2. So we have this set up right here. Any questions whatsoever about how to take this English sentence and convert it to these math symbols? Then once we're here, we're just back to that exact same process that we have been doing. We're going to verify that this right here is a z. It's not a z, so we're going to convert it to a z using our z-value formula. But now we've manipulated this formula a little bit for Chapter 6. Like I said, we're going to manipulate it a couple times this semester. This is one of the first times that we're manipulating it like this. Knowing that the denominator is not just sigma, but it's sigma divided by the square root of n. So now if we wanted to convert our x bar to a z value, what we're going to do is we're going to subtract mu sub x bar divided by sigma sub x bar. But whatever we do to one part of the equation, we have to do to all parts of the equation. So then we're going to end up with this right here. Substituting in the numbers that we got from part A, we're going to have 10.1 minus 9.43 divided by 1.2. We've now converted this middle part to a z value. And then to complete it, we're also going to include those numbers over here. Everybody good with this so far? If we do this arithmetic, this is going to give us 0.56 is less than z, which is less than 2.31. Again, if we look these two values up in our z table and subtract the smaller from the larger in order to get what's in between, we're going to end up with 2.773. Any questions about how to get 2.773? Everybody feel pretty comfortable with these types of problems? All right. Then what we're going to do is we're going to skip this one right here. Does anybody want to do that one? I don't want to just skip it without asking. Anybody want to do it? Everybody's good? Okay, then let's go on to the next problem, or the next section rather. The next section is purely theoretical. So, if this is your last math class that you ever have to take, and you don't ever go on and take stats, you can literally tune me out for like the next 2 minutes. And then I'll bring you back in. I'll show you the one thing that you have to remember out of everything I'm about to say. All right. So the central limit theorem is by far the most important thing in statistics, at least according to my opinion, right? If I had to pick one thing in statistics that takes the cake, it would definitely be the central limit theorem. Because this is what the central limit theorem says. The central limit theorem says, suppose you start off with a population distribution. Any one of these three population distributions are fine, but you can really come up with any population distribution that you want. So suppose for a second that you wanted to record everybody's height at UNC Charlotte. Or you wanted to go out and you wanted to record everybody's shoe size at UNC Charlotte. Or you wanted to go out and record everybody's 40-yard dash time, or what have you. Any characteristic that you could possibly come up with. If you wanted to record those things, chances are you would end up with a really funky distribution. Right? Might be one way for shoe size, might be the other way for 40-yard dash times, who knows. But we would end up with some funky distribution. Now, what we've been doing so far is this. We've always been boiling stuff down to z values. Because once we had z values, we could use our table. Right? Now, the problem with that is, when are we allowed to use z values? When can we use z? When it's normally distributed. Right? Again, if you go to our z table, at the top of the z table, we have this very, very, very specific graph that we can use this table for, and it's only for a normal distribution, right, for a bell-shaped curve. So we keep boiling stuff down to z values so we can use this table, but why can we use z values? Because our population distribution could be really, really funky, right? Like, especially in the real world. So how can we take these things and say, hey, we'll just change it to a z value and then we'll use our z value table? Well, the thing that allows us to do that is the central limit theorem. What the central limit theorem says is this. If we start taking samples from our distributions, kind of like we started taking samples of people in here, right, whenever we were taking groups of, how many times in a month you call your mother. If we start taking samples from these distributions, as our sample size starts to get larger and larger, our sampling distribution starts to look more and more and more like a normal distribution. To the point where once we reach a certain size for our sample size, our distribution is extremely close to a normal distribution. We're just off by like these tiny little decimal places. So, therefore, if we're now using a normal distribution, well, now we can start applying z values to it, right? This right here is an extremely important statistical concept. Because now what you're saying is this. Think of any kind of real-world problem that you want, or you have any kind of list of data that you want. You can plot that data on a graph, and chances are you're going to end up with something that's really funky. But now if what you start doing is you start taking samples of this data. And instead of recording each individual sample number, right, just like we did right here in how many times in a month you call your mother, if you take those groups and you start recording the sample averages of those groups, and you take all possible groups of a certain size, right, all possible groups of size 4 like we did earlier in the example in class, and you start plotting all of those samples, all of the sample averages. What it's saying is that it doesn't matter what your population distribution looks like. Your sampling distribution is always going to be normally distributed. And now we can start using z values, right? Now that's extremely important in the real world because what we're basically saying is that the central limit theorem, if we apply it correctly, allows us to use z values regardless of what our distribution looks like, our population distribution. And that's huge. So we can boil everything pretty much down to this table right here. Anything in the real world we could essentially just boil down to this, right? All right, so here's the main point that I want to get across to you guys. Now tune in for like the last 30 seconds so I can get this point across to you. The main thing that you have to worry about here is that it says if we have a sufficiently large sample size, and a sufficiently large sample size means that we have a sample size of 30 or greater. So here's the thing that you need to watch out for. Either the problem needs to say that your population is normally distributed, then we can use z values regardless, Or if it does not say that your population is normally distributed, we need to start having sample sizes of 30 or more so that we know that our sampling distribution is normally distributed, so we can apply z-values to that. So the main thing that you need to look out for is sample size of 30 or greater, unless it tells you your population is normally distributed. All right, is everybody good with that? Question?
So basically, you find a question that asks us, and it gives the sampling distribution about 28, and it could be,
Well, not yet. We'll get there in chapter 7. Yep, great question. So the question was, what happens if it's 28? Do we just stop there then? The answer to that is no, we're going to figure out how to do it if it's just 28 or something less than 30, but that's going to be in a subsequent chapter. All right, I'll see you guys on Monday. We haven't finished off chapter 6. We need probably about 25 minutes or for chapter 6, but the section that we haven't covered yet, there's only like 3 or 4 questions on your homework. So you'll be able to do the majority of it, but I'll push back the due date for you guys' homework.
Can you go over which ones we should study?
Sure. If you